Okay, thank you. Thank you. Thank you.
Okay, is Dr. Tanvi Saeed ready now? Please present your paper.
Thank you for inviting me in this seminar organized by Science and Technological Subcommittee of Bangladesh Awami League. Today, I would like to present my work on sludge and drained wastewater treatment, employing bioenergy producing natural treatment technology. That means constructed wetland. The first presenter already gave a brief introduction on constructed wetland. That means natural treatment technology. So I think it was coincidental. I didn't know that he would come here. So he already did my work, my initial work. So I can move now directly. Constructed wetlands, actually, I will give a very brief introduction. It's a natural treatment technology. It uses media and plant, and inside the media and around the root zone, bacteria, they grow, and also other types of microorganisms like fungi, protozoa, but bacteria, they are the main plant. So when wastewater passes through the media, the water pollutants are absorbed or are removed by the bacteria. And moreover, plants, they uptake nutrients, for example, nitrogen and phosphorus for their growth, and if metals are present. And the media, the chemical properties of media, they also absorb pollutant. But again, for the macro pollutant, for example, nitrogen, phosphorus, BOD, COD, or solid, the mainly BOD, COD, solid, nitrogen, the main customer is bacteria. Whereas for phosphorus, this media, it plays an important role. And for metals, media and plants, because the metals are in wetland system, they are removed by physico-chemical process. Okay. Now I will talk about sludge treatment. Now, what is sludge? Sludge, it can be of many types. For example, human waste. It goes into the septic tank or maybe to the treatment plant. We call it fecal sludge. Here I will talk about the drinking water sludge. That means in our Saidabad drinking water treatment plant, they intake water from Shitalokha river and they treat it. So they use different types of chemical to allow the sedimentation of solid. And those chemicals and solid, they precipitate inside the system, that is sludge. And that is very dangerous for environment. So I will talk about how to treat this sludge. Okay, so this is a typical sludge treatment wetland. You see, in the upper portion, you will see the sludge accumulated. We do sludge and it is being accumulated. So the first action, what will happen? The evaporation, the effect of sunlight. Due to the effect of sunlight and due to transpiration activities, we call it together as evapotranspiration. Plants will extract sludge-bound water because sludge, it contains only 1 to 10% solid and all are liquid. So plants, they are extracting solid. And during the sludge drying process, what will happen? Water will come out, so it will move through the media. And when it moves through the media, bacteria will remove pollutant. And also the media will absorb pollutant. So this is a very brief idea. Now I will introduce a very new system, that is microbial fuel cell treatment wetland. So this is a variation of the constructed wetland that I showed you. Here we are integrating electrodes. So what will happen? Bacteria here, the electrogenic bacteria, that means the bacteria, what will happen? They are capable to produce electrons. Bacteria will degrade organic matter and they will produce electron. Okay, these are electrogenic bacteria, but they will occur or they will work only when we insert electrodes. That means anode and cathode. So we have inserted anode and cathode and we connected it with resistor and multimeter. So in the bottom portion, that means anaerobic portion, the organic matter will be degraded by the electrogenic anaerobic bacteria and they will produce electron. The anode will capture that electron, pass it through the resistor, and the cathode will capture it. And in presence of oxygen, the circuit reaction will be completed and we will get electricity. So this is the microbial fuel cell wetland. It has been introduced only 10 years ago. Now it's a hot topic. So what is microbial fuel cell sludge treatment? So actually this is the same thing. What we have seen here. What in microbial fuel cell sludge wetland, what will we do? We will integrate electrodes again. Any electrode that is capable to capture electron. It can be aluminum, but steel and graphites, these are the best metals to capture electron. But here we are using we have used aluminum because it is cheap. So our objective is to treat the sludge so that we can apply it on the land. And also another objective, the wastewater that is produced from sludge treatment, also to treat it because we have to discharge it. So there are two objectives, sludge and wastewater. So this is very complicated, sludge treatment wetland. This was our operational diagram. Actually, this is an outcome that we published this year in Chemical Engineering Journal, impact factor 16.7. I was the lead. So I'm just presenting that result. These are our setup. Number one setup, it is unplanted. Number two, we have planted. And number three, we have planted and also we have earthworm. Earthworm means kecho. I will tell you why we need kecho. And number two is again electrode integrated wetland. And number five is same, but again here we are introducing earthworm. So we are actually examining defined combination to find out which system works best. These are the defined types of media we have used. You see, in the bottom layer, we have used large stone so that wastewater comes out. And it can be, it facilitates the effluent drainage. And in the middle layer, we have used sand, sorry, small stone, and in the upper layer, sorry, in the uppermost layer, we have used sand. And then we have introduced sludge, okay? And these are the plants that we have used, phragmite, very common plant. We can find it near the lakes. And these are the electron components. That means the aluminum plate, anode and cathode wires, and multimeters. This is the Saidabad drinking water treatment plant, the plant that supplies water to us. But look at the sludge management. See, they are using acres or hectares of land. They are just discharging sludge, but they do not know what to do with it. So we do not know what is the environmental condition in that area. Okay, so you see, haphazardly managed, and this is very dangerous. This is causing a danger to the environment, to the adjacent environment, maybe to the whole area. We don't know. Our sludge operational protocol, we conducted the experiment for 26 weeks. Okay, and the sludge that we collected from here, you see, it's extremely liquid. You see, it's extremely liquid. Only 1.5% solid content, and the sludge loading rate in these wetlands here in these wetlands 30 kg total solid per meter square per year. This is the standard procedure. So how we operated the wetland? Each week we applied sludge for 2 consecutive days. For example, we applied sludge on Sunday and then we applied sludge on Monday. And the remaining 5 days is resting period. So why resting period? Because during resting period, what will happen? The water will come out from the sludge and it will be stored in the, here, if you see the diagram, it will be stored in the bottom of the tank, the water. And after 7 days, we have opened the valve and we extracted all the drain water before we apply the next batch. Now, if you apply sludge continuously, for example, 30 times a day, so you won't have time, you won't give sufficient time to dry up the sludge. So this is very important. Feeding followed by resting, feeding followed by resting. This is one mistake that we make in sludge treatment, and then the system fails. Okay, so this was our experimental system. You see the 5 experimental system that what I have shown here at University of Asia Pacific. This was the initial condition, and look at the matured system after near the end of the experimental protocol. These are the parameters that we have measured for the water that came out from the sludge. And those are the parameters that we measured for the sludge that we got on the top of the wetland due to drying process. We have not measured metals because this was a drinking water treatment plant. Look at the sludge properties, like ammonium, BOD, COD. Look at the COD, somewhere around 3000 milligram per liter, but the effluent discharge only 20 milligram per liter. So the concentration of sludge here is 100 or maybe 200 times higher than the discharge criteria. So this is extremely dangerous for the environment. Now we have found some result. I'm just presenting some result in brief. So after the treated water came out from the wetland after 7 days, this is very much aerobic. You see the dissolved oxygen was in the very upper range, greater than 7 milligram per liter. So it indicates good treatment by the wetland. And look at the effluent BOD concentration. The BOD concentration was almost 20 milligram per liter, or some wetlands even achieved below 20 milligram per liter, the water. That means it is very much safe. It made the BOD discharge guideline. But we have not found any significant difference between the systems. That means we have not found that, okay, the planted system was better than the microbial, or the planted microbial with earthworm was better than the planted. So all system was almost equivalent in terms of BOD removal. But most importantly, they met the discharge criteria. But when we go for the, this is, I think, ammonium here, the ammonium concentration, look, it is below 5 milligram per liter. So it made that easier discharge criteria. Here, we saw that the microbial fuel cell, if we go back, this system, I will show this figure for once and then I will refer. This system, S5, the microbial fuel cell with earthworm. This was the best system for nitrogen removal because what is happening, earthworm, they have burrowing capacity. They create crack on the sludge. So atmospheric oxygen goes inside the wetland system, and that helps the aerobic bacteria, that means nitrifier, that removes the ammonium. So it was better than the other systems. Okay, but the other systems were also better, but the microbial fuel cell with earthworm, they perform better. And also the anode material, that means the anode material, ammonium oxidation occurred around the anode plate. Okay, so it also improved ammonium removal of this system. Okay, so I think now we can, I will not come back to this slide because now, and similar to the total nitrogen, in total nitrogen also, the microbial fuel cell earthworm assistance system, it has achieved very better total nitrogen removal. But TP removal, phosphorus removal was almost equivalent for all systems, because as I told you, phosphorus removal in wetland system, it occurs by absorption by media. Any media that contains calcium, aluminum, or iron, it will absorb phosphorus. Okay, so we have to be tricky. If you want to remove phosphorus in wetland system, you have to use media that contains either calcium or aluminum or iron, because they will form precipitate with phosphorus and will precipitate. And this is another important objective, the total solid content, because in any sludge treatment process, the main objective is to increase the total solid content before you can apply it to the land. Because the main sludge, it contains 1.5% to 2% solid, solid and 98% water. So it will massively pollute the environment. So you need to release that water and increase the total solid content. And after the drying period, we have followed 60 days drying period. You see, we have achieved satisfactory TS removal above 80% for all systems. And again, this microbial fuel cell wetland with earthworm, it achieved very high, better TS removal, almost above 90%. That means it is very good for land application. But again, I'm not telling that you can use it for agriculture, because for agriculture purpose, we need to measure some other parameters. For example, we need to measure whether metals are present here, or whether sodium, aluminum, some ions are present here. If these meet the criteria, then we can say, okay, this might be applied for agriculture. But our objective was not for this research, was not for agriculture. Our objective was to safely dispose it on the land. Okay. And this is the organic matter, nitrogen and phosphorus content of the sludge. It has been significantly reduced. You see, the feeding period means when we were applying sludge, the nitrogen, organic, and phosphorus, it was accumulating when we were applying sludge. But when we went to the drying phase, that means we stopped feeding the sludge. What happened? The concentration was reduced because some internal microbial reaction, complex microbial reaction occurred that reduced the pollutant, organic, nitrogen, phosphorus. So that means we are modifying or improving the chemical properties of the sludge. And this is the voltage production from the planted system or the microbial fuel system. We see we are getting some power or some voltage, although it is very minor because the scale was minor. But again, our objective was not at this stage was not to produce electricity or not to enlighten the bulbs or all these things. Okay, but this we are producing electricity. So the planted microbial fuel cell without earthworm, it was producing better voltage than with earthworm, because again, earthworm, it has borrowing activities, and when oxygen enters, it disrupts the electrochemical organic matter oxidation. That's why the microbial fuel cell planted without earthworm, it produces higher energy. And the current density, again, power from the polarization camp, same thing. The planted microbial fuel cell was better than the earthworm assisted system. But our main conclusion is we can use this constructed wetland system, whether you may integrate electrodes or you may not integrate electrodes. You can simply use planted system, follow some simple schedule, 2 days or 3 days dosing followed by 4 days resting period, and you can manage the sludge. So we have provided the solution to WASA, and now it's up to them what they will do. Thank you very much.
Thank you, Dr. Tanvir. And we can take 2 questions now.
Many parameter. In your last parameter, just coliform. You indicate here initial coliform is 10 to the 3 CFU per 100 ml, but you didn't show any result after the treatment. What about your coliform concentration?
You will find it in our paper. It was almost, I didn't show it to reduce the content, but we have significantly reduced, and some systems also achieved 97, 98, 99% coliform removal.
96, 97.
98, 99.
That means it's a 1 log. Still 2 log is available in the environment.
Now 2 log, in, of course, there is
no, because 90% is 1 log.
No, you need to understand, because in any system, you will achieve 99%. That means you will have again 1 log system that you need to achieve through disinfection. And you can achieve that through surface flow wetland.
Okay. Any more? Yes, please. Yes. This is fine. No problem.
Sir, I want to ask, you already touched the point. Say if there is a lack of DO in your system, I mean, you use earthworm for the availability of DO, I mean, the oxygen in your system.
Actually, we introduced earthworm because it has burrowing activities. It will create crack, and it will additionally facilitate the transmission of oxygen inside the media. But another source of oxygen is plant in wetland system, because these fragmite plant, the roots, they release oxygen inside the media. So that is a source. And also during the drying process, when that means like when the media is dry, atmospheric oxygen, what will happen? It will enter inside the media. But when if you operate this continuously, for example, 7 days a week without anything, you will find significant decrease of dissolved oxygen. Maybe you will see 0.5 milligram because oxygen is not entering due to saturated media. But here, that's why I was telling that you need to follow schedule, 2 days, maybe feeding, resting. If you continuously feed sludge, they won't get time to release the water. So what will happen? Sludge will be accurate, but that will be wet sludge. And again, the bed will be anaerobic. So the aerobic reaction, for example, nitrification, it won't occur. You won't be able to remove nitrogen. So this has to be maintained. And another system is maybe there are many artificial systems. You can passively also supply oxygen, but for this research, we didn't use the passive oxygen source because again it uses energy, so it will create some complexity. So we wanted to avoid all types of external electrical devices, the consumption devices. But again, aeration could be another feasible option.